Today, I'm presenting our research on securing mobility predictions in 5G networks using AutoML. In 5G networks, the Network Data Analytics function, or NWDAF, uses machine learning to predict where mobile devices will move next. This is crucial for optimizing network resources and reducing signaling overhead. The challenge is that NWDAF models need periodic retraining to maintain accuracy. But what happens when malicious devices inject corrupted data during this retraining? Our research investigates whether AutoML can help operators build models that remain robust against such attacks. We focused on what we call the tuple jump mobility attack, the most effective attack from previous research. Here's how it works. An attacker obtains multiple devices and clones them with identical subscriber identities. They arrange these cloned devices in pairs near different cell towers. The attack creates fake mobility patterns by having one device connect while its clone stays silent, then switching roles. This makes it appear as though a single device is jumping erratically between distant locations, when in reality both devices remain stationary. This attack is practical because it requires no physical movement, just strategically placed devices. Our threat model assumes the operator cannot distinguish these adversarial patterns from legitimate user mobility, leading to data poisoning during model retraining. We tested with varying proportions of adversarial devices, from 0.5% to 10% of the total device population. We used Ericsson's mobility simulator based on real network topology from India. The data shows device connections to cell towers over time, with signal strength measurements. Our dataset includes 10,000 legitimate users following predictable home-to-office patterns, plus varying numbers of adversarial devices performing tuple jump attacks, from 50 to 1,000 malicious devices. We pre-processed the raw data into features like previous connected towers, connection durations, time of day, and neighboring towers. Then we configured 3 AutoML frameworks: FLAML, AutoGluon, and AutoSclern. The key test: we trained models on clean data using either 6-minute or 60-minute time budgets, then retrained with poisoned datasets containing adversarial mobility patterns. This shows whether robust initial model selection with AutoML outperforms frequent model reselection when facing data poisoning attacks. Next, I'll demonstrate the AutoML framework logs, showing model generation under different conditions. We'll examine FLAML's behavior, both during normal operation and under attack scenarios. First, the baseline scenario with no attack. Here, we see FLAML searching for the optimal model configuration with a 60-second time budget. The framework generates 2 complementary models. One predicts the next cell tower location for each user equipment, while the other estimates how long the UE will remain connected to a particular E node B. We calculate the combined accuracy by integrating predictions from both models. Second, the attack scenario. This shows FLAML's model selection process when tuple jump attacks are actively occurring during training. We extended the time budget to 360 seconds as specified in our methodology to allow for more thorough model exploration under adversarial conditions. The framework again produces 2 models with combined accuracy metrics, allowing us to compare robustness against the baseline performance. The future work for this will be about finding a new detection method under similar circumstances. Thanks for listening.